Okay, let's dive right into this explainer and tackle what is honestly one of the most mind-bending cosmic mysteries in all of modern physics. We're talking about the holographic paradox. Are we just a black hole's memory? Today, we're going to unpack a concept that basically challenges everything you think you know about the physical world. Space, time, reality itself. Prepare to question the very dimensions you live in. So, I want you to just look around you for a second. Your desk, your hands, the room you're sitting in right now, it all feels incredibly solid, right? Unmistakably three-dimensional. But what if it isn't? What if this entire 3D universe we experience is actually just a shadow, a projection of a two-dimensional reality? Now, I know that sounds straight out of science fiction, kind of like Plato's cave, where we're all just sitting around watching shadows on a wall. But in the realm of theoretical physics, this is a very serious, highly debated mathematical framework. To understand exactly how physicists got to this crazy idea, we have to define our core concept, the holographic principle. It suggests that all the information contained within a three-dimensional volume of space can be perfectly represented or encoded on the two-dimensional surface that encloses it. And it is absolutely crucial to understand that, in physics, this is not just a fun metaphor. It's a literal mathematical possibility. Think about how a physical hologram stores a fully 3D image on a flat, 2D sheet of plastic. The universe might literally store the information of our entire 3D reality on a 2D mathematical boundary. Section 1. The crime. The information paradox. Every good detective story has to start with a crime, and our cosmic crime scene was actually discovered by the brilliant Stephen Hawking back in 1975. Up until then, standard physics essentially dictated that black holes were the ultimate cosmic vacuum cleaners. Nothing escapes, period. But Hawking applied quantum mechanics to the edge of black holes and realized something absolutely shocking. Black holes aren't completely black. Because of quantum effects near the event horizon, they actually emit a very dim glow. And over incredibly long periods of time, this Hawking radiation causes the black hole to lose mass, shrink, and eventually just completely evaporate into nothingness. And right here is where we find our crime scene. Because if a black hole eventually vanishes, what happens to all the physical stuff that fell into it over billions of years? Or more specifically, what happens to the quantum information that made up that stuff? See, there's a fundamental rule of quantum mechanics called unitarity. It basically states that quantum information can never, ever be destroyed. You can scramble it, you can burn it, you can crush it, but the core information itself must always survive. So if a black hole just evaporates and takes all that information out of existence, that breaks the most fundamental laws of quantum physics. And this massive problem became known as the black hole information paradox. Section 2. The clashing titans. This conflict perfectly framed the ultimate stakes of modern physics. It was a heavyweight clash. In one corner, we have general relativity, Einstein's absolute masterpiece describing macroscopic gravity, where black holes are basically bottomless pits. And in the other corner, we have quantum mechanics, the rulebook for the subatomic world, which strictly demands the absolute preservation of information. Now, Stephen Hawking actually stood on the side of gravity here. He argued that, yep, the information is truly lost and quantum mechanics just needs to be rewritten. But physicists like Leonard Susskind and Gerard 't Hooft, no way. They refused to accept that. They knew that if quantum mechanics fell, the entire foundation of modern physics would just collapse with it. They had to save the information. Let's look at how this scientific war really escalated over time. After Hawking dropped his bombshell in '75, the paradox just kind of simmered for years. But then, in 1993, Gerard 't Hooft proposed a radical, honestly almost crazy idea regarding black hole thermodynamics. 2 years later, in '95, Leonard Susskind took that idea and refined it into what we now call the holographic principle. And by 1998, Juan Maldacena published a paper so profound that it literally became the most cited paper in high-energy physics. It brought holography right into mainstream string theory. Section 3. The 2D twist. So Susskind and 't Hooft realized something truly profound. To save the information falling into a black hole, you actually had to stop looking inside its 3D volume altogether. In Suskind's original 1994 paper, he argued the universe can be mapped sort of like a projection. Imagine a single fundamental particle, a parton, just sitting out there in 3D space. Well, mathematically, its exact location and state can be perfectly projected and recorded by a light ray onto a distant, flat 2D screen. It's a mathematical mapping where absolutely zero data is lost. And this brilliantly illustrates their ultimate conclusion. When you apply this projection concept to a black hole, the entire 3D interior is perfectly mapped to a 2D surface. The math, which uses something called the focusing theorem of general relativity, shows that the information density never exceeds 1 bit per Planck area. To put that simply, all the 3D stuff inside the black hole leaves a perfect, intact 2D imprint right on its outer boundary, the event horizon. And just like that, the initial crime is solved. The quantum information of whatever falls into a black hole isn't destroyed at all. It's just caught and perfectly preserved as a 2-dimensional hologram on the black hole's surface. So when the black hole eventually evaporates via that Hawking radiation, the information is slowly scrambled and released safely back into the universe. The paradox was so cleanly resolved by this holographic math that in 2004, Stephen Hawking actually conceded his bet. He publicly admitted that, actually, black holes do not violate quantum mechanics. Section 4. Expanding the illusion, ADS-CFT. But here's the thing. The story doesn't end with black holes. This math was so elegant, so beautiful, that physicists had to ask, well, if a black hole is a hologram, could the whole universe be one too? The massive breakthrough here came with Juan Maldacena in 1998 with something called the ADS/CFT correspondence. Now, don't let that acronym intimidate you. Just think of it as a mathematical Rosetta Stone. Maldacena proved that a 3D space with gravity, which physicists like to call the bulk, is mathematically identical to a 2D space without gravity, the boundary, which is governed purely by quantum mechanics. Basically, if you've got a physics problem involving gravity that's just way too hard to solve in 3D, you can use this dictionary to translate it into a 2D quantum problem, solve it there easily, and translate the answer back. It's a real game changer. New York Times science reporter Dennis Overby came up with an absolutely brilliant way to visualize this, and it really hits the nail on the head. Imagine a can of soup. All the 3D stuff, the galaxies, the stars, your house, you, me, we make up the thick, messy soup inside the can. But all the fundamental quantum information that perfectly describes every single piece of that stuff, it's actually inscribed on the 2D label on the outside of the can. We feel like we're happily swimming around in the soup, but fundamentally, mathematically speaking, we might just be the label. Section 5, the interrogation, testing the theory. So, the big question, can we actually test this whole shebang? Is there any physical evidence? Well, scientists have certainly tried. Over at Fermilab, they built a $2.5 million machine called the Holometer. It tried to detect a quantum jitter in space-time. Essentially, they were looking for the literal pixelation of our 3D universe. But that experiment ended in a null result. They didn't find anything. However, when astronomers looked at data from the Planck satellite, which measures the cosmic microwave background, basically the lingering heat from the Big Bang, they found something amazing. The slight temperature fluctuations of the early universe actually fit the 2D holographic mathematical model slightly better than they fit the standard 3D cosmological model. So, while it's not absolute proof, it is highly, highly compelling evidence. So what should you actually take away from this explainer today? First off, the black hole information paradox, it's essentially solved. Information isn't destroyed, it's stored holographically. Second, the math firmly proves that a 3D reality can be perfectly encoded on a 2D boundary, which wonderfully connects gravity and quantum mechanics in the process. And ultimately, it points to a wild conclusion: gravity itself might just be an emergent illusion. Which leaves us with this final, lingering thought. Look at your hands one more time. They feel real. They feel completely solid. But the deepest, most advanced math we currently possess suggests otherwise. Are we, and everything we have ever known or loved, simply an incredibly complex projection? Are we really just information, mathematically encoded on the distant 2D edge of the universe? It's a massive question, and one that theoretical physicists are going to be wrestling with for decades to come. Keep questioning your reality, and I'll see you in the next explainer.